In this video, we're going to talk about differentials and delta notations. Let's get started with the delta notation for the function y equal fx. Recall that the difference quotient of the function f is actually the quotient of the difference f of x plus h minus fx over h. Remember that h is actually also the difference between x plus h minus x. Well, therefore, we only care about the difference of the variable and the difference of the corresponding value of the functions. So in order to simplify the notation, well, now let's denote the denominators, the difference between the corresponding value of the function f by delta y, and by delta x we mean x plus h minus x, or h. So here delta is actually the letter D in Greek. It stands for difference. So basically we can depict the delta notation using the graph of the function y equal fx, and remark that delta y over delta x is actually the slope of the secant line connecting the 2 point P and Q in the graph of the function f. And note that in the formula delta y equal fx plus h minus fh, if we actually substitute for h delta x, then actually we get delta y equal to f of x plus delta x minus fx. So let's move on to differentials. Okay, recall that the derivative of f at x is defined to be the limit of the difference quotient when h tends to 0, if this limit exists. And so with the help of the delta notation, we can actually simplify the formula by writing that the derivative of f is actually the limit of delta y over delta x for delta y approaches 0. And because we write y equal fx, so remember that we also have the Leibniz notation for the derivative of f, which is dy over dx. So until now, we just think about dy over dx as a symbolic notations, and it does not have any meaning of a real quotient that we know of. So in order to make it an actual quotient, we're gonna define the differentials. So first, let dx stand for delta x, and we call that the differential of x. And then by dy we mean that it is a product between the derivative of f at x times delta x. Then this is called the differential of y. So we already have the delta notation and the differential notation, and all of them can be depicted in the following pictures. We see that dx is actually the same as delta x, and here dy is actually the difference between the y coordinate of the point lying on the tangent line and the point lying on the horizontal line with the y coordinates is equal to f of x1. Okay, so actually the quotient dy over dx is nothing but the slope of the tangent line to the graph passing through the point with coordinates x1, fx1. And whereas delta y is actually the difference between the two corresponding value of f. Let me remind you that delta d of y over d of x is actually the limit of delta y over delta x for delta y tends to 0, right? So for small value of delta x, it is reasonable to think that dy is reasonably close to delta y. And let's take a look at real example to see that why we have this kind of approximations. For y equal x times 4 minus x power 3, we now want to find out what is dy and try to compute dy in a specific example where x equals 5 and dx equals 0.01. And finally, we want to compare dy to delta y. Okay, so first, if we want to compute dy over dx, then actually there's a Leibniz notation for the derivation. So we just need to take the derivative of x times 4 minus x power 3. So now actually we see that inside the bracket, the function that we want to take the derivative is actually the product of two other functions. The first one is x and the second one is 4 minus x power 3, and let me just colorize this so that you can see what is the first and what is the second functions. Okay, so now using the product rule for computing derivatives, then is actually the derivative of the first one times the second one plus the first one times the derivative of the second one. Okay, so with the help of the color, you can easily see which term coming from which. Okay, the derivative of x is actually 1. So it's very easy to see that the first term becomes 4 minus x power 3, right, plus the second term where it is a product between x and the derivative of 4 minus x power 3. So the derivative of 4 minus x power 3 can actually be computed using the extended power rule. So if you don't remember the extended power rule, then actually it is just a special case of the chain rule. Now think about 4 minus x as a variable z. Okay, so z is now a function of x. If you want to compute, z power 3 is actually 4 minus x power 3, right? So it's actually here we have the composition function between z power 3 and 4 minus x. So if we apply the chain rule, now it's become d over dz of z power 3 times dz over dx. And now it should be very easy to compute the corresponding derivative, which is nothing but x times 3 times z squared times minus 1, because z is equal to 4 minus x, so if you take the derivative with respect to x, it should be minus 1. And now to obtain the final result, you just need to substitute 4 minus x for z in the last formula, and so we get the desired computation, which is now 4 times 1 minus x times 4 minus x squared. Okay, so just by multiplying both sides with dx, you get what we need as a formula for dy. Okay, so now if you want to evaluate dy at some specific value of x and dx, okay, then note that because we have the formula for dy, so the evaluation should be quite easy. And with the help of a digital calculator, you can easily compute dy to be a minus 0.16. So we are left with the last task of comparing dy to delta y. So for this, we need first to compute delta y. Okay, so now the information that we have is x equal 5 and dx is equal 0.01, and delta y is actually the difference between f of x plus delta x minus f of x. So delta y is actually minus 0.16 something. Okay, and if we want to compare dy to delta y, we just need to take the difference between them, which is now minus 0.00180801. So actually this value is significantly small, It means that delta y and dy are reasonably close. We justify the observation we made that for small value of dx, then dy is actually a good approximation of delta y. Okay. Now let's get a closer look at this approximation. Okay. First, on the right hand side, you know that dy is actually the product between the derivative of f at x times dx. On the other hand, on the left hand side, delta y is actually the difference between f of x plus delta x minus fx. So we can add both sides with fx and get the formula that f of x plus delta x is reasonably close to the sum of fx and the product of the derivative of f times dx. So normally in practice it is easy to compute fx and f prime of x. So the right hand side can be computed quite easily, whereas the left hand side is actually more complicated to compute. So this is a good and useful approximation of computing f of x plus delta x. So in business, if we consider the cost, the revenue and profit functions from the production and sale of a number of items that we denote by x, then, well, x here is must be an integer value, right? So if we let delta x to be 1, which is the smallest possible difference between two consecutive items, then the approximation formula now become c of x plus 1 is approximately the sum of c of x plus c prime of x, and similarly for the revenue and the profit functions. So this actually gives a good way to approximately calculate the value of the cost, the revenue or the profit functions of producing and selling the x plus 1 item from that of x item. Okay, so for this reason, the derivative of the cost function, the revenue function, and the profit functions have a specific significance. For this, we call c prime of x the marginal cost at x. It is the approximate cost of the x plus 1th item. And similarly, we call r prime of x the marginal revenue at x, and it is the approximate revenue from the x plus 1th item. And last, we call the derivative of the profit functions at x the marginal profit at x. It is actually the approximate profit from the x plus 1th item. Okay, so now let's look at an example to see how actually we can compute the value of marginal cost, revenue, and profit. So given the cost and the revenue functions as here, then we need to find each of the following informations. The first, we need to determine the total profit Px, and then try to find the total cost, revenue, and profit from the production and sale of 50 units of the product. And last, we come to the problem of determining the marginal cost, revenue, and profit when 50 units are produced and sold. Okay, so now let's get to the problem of computing total profit. It should be easy because the total profit is actually the difference between the total revenue and the total cost, and these in turn are already given using a specific formula, so that just by substituting these formula for Rx and Cx, we can easily see that P of x is actually a polynomial function, a cubical one, which is x power 3 minus 74 times x squared plus 40 times x plus 27,490. Okay. So now we have the formula for the cost function, the revenue function, and the profit function. So we are ready to make evaluation. Now C50, the first thing we need to compute is 62 times 50 squared plus 27,500, and this can be easily seen to be $182,500. And similarly, we can compute the revenue at x equals 50, which is $97,010. And last, the profit P50. Now, actually, we do not need to evaluate P at 50. We only need to take the difference between R50 and C50. So this gets us minus of $85,490, which means that after the production and sale of 50 items, we lose a lot of money. Okay, so now let's see what is the marginal cost after the production and sale of 50 items. For this, we just see that, recall that actually this is the derivative of C evaluated as x equals 50, right? So first we need to compute the derivative of C, which is the derivative of 62 times x squared plus 27,500. And it is just a quadratic function, so the derivative should be taken quite easily, and it is 124 times x. So for this, once 50 units have been made, the approximate cost of the 51st unit, or the marginal cost, is actually C prime of 50, which is the product between 124 and 50, and this can easily compute, and is $6,200. Now similarly, we compute the derivative of our x, and it is 3 times x squared minus 24 times x plus 40. And so the marginal revenue is at R prime of 50, which is $6,340. And last, the derivative of the profit function is actually 3 times x squared minus 148 times x plus 40. And so once 50 units have been made, the approximate profit from the sale of the 51st items, or the marginal profit, is actually pre-prime of 50, which is $140.